I'm glad to inform you we're going to start talking about a new topic. The new topic is the old topic plus another integral. So we're talking about the triple integral now. Now, you might say, we have learned the single integral and we have learned the double integral. Why do I need to learn the triple integral? Well, the idea is that we are dealing in multivariable calculus. I never said anything about two-variable calculus. We're doing multi. So we need to expand this to triple integrals, right? So we're dealing with the triple integral. Now, I should preface this by saying that there is no limit to how many integrals we can do. We could do infinitely many integrals, assuming you can get the bounds correct, if that's something you want to do. For example, in special relativity or in general relativity as well, you deal with space-time. Now, space-time is something that takes in our three-dimensional world, but it also adds a time dimension, so everything moves through a four-dimensional world. And you're going to need to integrate things in order to determine what the dealio is with your system. So you're going to need to use a quadruple integral. So you do an integral over all four dimensions. So you do d4x, right? So that's an integral over four dimensions of whatever you're dealing with in there. Okay, so why don't we look at what the triple integral is and how we can use it with an example in the Cartesian product. Let's get started. The definition is that if I have an integral over some box B, then I can say that the triple integral of x, y, and z with respect to a differential volume is equal to the limit of the sum of the ijkth x area, the ijkth y area, and the ijkth z area, all with respect to delta v, delta volume, right? Now this is the triple Riemann sum. The Riemann sums get progressively harder as you go up in dimension. We all remember that it was very tedious to even do a single Riemann sum when we started integration in single variable. And we dared not even look at a two-dimensional Riemann sum. You don't even want to see what the three-dimensional Riemann sum is. So we're going to want to integrate, and of course to do that, we use some other theorems. So let's say that B is defined as the Cartesian product between A and B, C and D, and R and S. Then we can say that the integral over f dv is equal to the integral between R and S, integral between C and D, integral between A and B of f of x, y, and z, dx, dy, dz. Now this is Fubini's theorem for triple integrals. Of course, what that means is that you can interchange these values of integration if you're dealing with a Cartesian product in order to make your lives easier, right? So why don't we try an example for a single, for a box case, right? So if you remember in double integrals, we had general regions. So we had the rectangular case where we could have region R, right? But then we also had cases where we could have like type 1 regions or type 2 regions or polar regions. We're going to get to that later, but now we're going to be dealing, the analog of the rectangular region is the box region. So we integrate over a box, and then you're finding, I don't know, a weight quantity or something like that. It's hard to visualize because you're going to be kind of finding something in the fourth dimension. So there's no nice way to visualize a triple integral, unfortunately. Let's evaluate the integral of x, y, z squared dv on b equals 0, 1 times negative 1, 2 times 0, 3. So what we have here is we have the integral of f dv is equal to the integral, let's integrate dx, dy, dz between 0 and 3, then between negative 1 and 2, then between 0 and 1 of x, y, z squared dx, dy, dz. Then we get integral between 0 and 3, then negative 1 and 2, then 1/2 x squared y squared, x squared y z squared, there shouldn't be a squared there, all between 0 and 1, dy dz. Then we get between 0 and 3, then between negative 1 and 2 of 1/2 yz squared dy dz. And finally, we can do more fundamental theorem of calculus, integral between 0 and 3, 1/4 y squared z squared between negative 1 and 2 dz. Finally, integral between 0 and 3, 3/4 z squared dz, which is equal to 1/4 z cubed between 0 and 3, which is 27 over 4. Okay, so as you can see, it's just another step. It's another iteration in the integral that we need to deal with. Now, something that's important to note is that you can have 6 different combinations of what this could look like, what your differential element could look like. And again, that's what's nice about multivariable. You can choose your path. You can choose what's going to be easiest for you, and then you can make the decision on your own. What should I integrate with respect to first? And then your decision might prove helpful. Sometimes it might prove not so helpful, but it usually works out. All right. In the next video, I want to start talking about general regions for multivariable triple integrals, and then we will talk about applications. And the way that we're going to kind of structure talking about triple integrals is that we have 3 different coordinate systems that we can deal with. For double integrals, we had rectangular, and then we had polar. Well, here we have rectangular. These are the ways you can divide up 3D space. We also have cylindrical. Then we also have spherical. And we're going to talk about rectangular first, then we're going to talk about cylindrical, then we're going to